In this video, we are going to talk about ringing because it's like kind of like simplest simulation what people may do or what they may want to do when they are doing PCB layout. And also we will have a look on real measurements. We will compare the real measurement and the simulation of this ringing, and we will talk about the things which are important to get really good results from the simulations. Is that what we are going to talk about, Eric?
Yep, that sounds like a great plan.
Okay, so first, why this ringing may be interesting for us. I know from my experience, when I sometimes when I do PCB layout, there is a track which has to go to multiple pins. It may be quite long, and then we can see this ringing, correct?
Right. Yeah, I kind of look at there's a boundary in when you think about the design of interconnects when you have to worry about reflection. Ringing is well, there are a couple sources of ringing. One of them is ground bounce, which is just about inductance and kind of lumped behavior. The other kind of ringing is from reflection noise, and they have completely different root. They look kind of the same sometimes, completely different root causes, completely different solutions to fix those problems. So we're talking about the ringing problem that arises because of reflections in transmission lines, and so that occurs in situations where the rise time is short enough or the length of the interconnect is long enough. It's that product that you have to worry about. And rough rule of thumb is if the rise time of the signal is longer in the rise time of the signal in nanoseconds is longer than the interconnect in inches, then all the ringing, it always happens, but it's smeared out. You never see it. It's a who cares. And so that means, if you got a nanosecond rise time signal, you're talking about any interconnect longer than an inch, a couple inches long, and you may see ringing. It is a possibility. You have to worry about it. Whether it's a problem or not depends on your analysis, but you should analyze it if that's the case. So, and it's all about reflections from, and the only thing that causes reflections is changes in the instantaneous impedance. And that's going to happen mostly at the launch and at the transmitter and at the receiver. And reflections are an absolute basic fundamental property of, signals moving down an interconnect and encounters a change in that instantaneous impedance, it's going to reflect. Whether it's a problem or not, well, you have to put in the numbers to evaluate how much overshoot or undershoot you get.
That's why we would like to create these simulations, for example.
Right. Yep.
So,
and so, sorry, go ahead.
No, you can finish.
So there are really two kind of levels of analysis. The first is, put in those with simple estimates, rules of thumb, piece of paper, some calculate. The first is this rule of thumb of, hey, if the interconnect is longer in inches than the rise time in nanoseconds, then it says, okay, you got to put in the numbers. And unfortunately, other than the absolute simplest case, it's really hard to do the analysis of reflections with pencil and paper, because you have to keep track not only of the voltage as it moves back and forth and reflects, but you have to keep track of the rise time of the signal as well. And it's just really hard to get any realistic estimate of how bad the ringing is unless you use a simulator. And the most important simulator, in fact, the analysis I'm going to show you here, any circuit simulator that has a transmission line element in it can be used. Right now, so I teach a freshman circuits class, and I try to introduce them to simulator tools. And historically, we've used LT Spice, which is, it's been around forever. It was developed by Mike Engelhardt at Linear Tech, and so this was called LT Spice. And then they Analog Devices bought it, and then Mike moved on, and so LT Spice isn't really supported much. It's still an old interface. Mike actually moved on to develop a later version of LT Spice, which he worked with Cuervo on, and the later version that Mike did is available from Cuervo, and it's called Q Spice, also free. And so that's available. I find Q Spice is a little bit more advanced. It's not suitable for an introductory spice, but my favorite free Spice tool right now is Symmetrics. And there's a free version, it's called Symmetric Elements. It's free, and it is really easy to use. Great graphics and a lot of great models in it. Understands transmission line elements, and so all of the simulations that I'm showing here and that anybody could do, you could literally use the free version of Symmetric Elements to do. And then if you really get into this stuff and you say, wow, I've got my board and it's got a lot of microprocessors, FPGAs, or it's got a lot of digital logic on it, and I'd really like to simulate the whole system here, then I recommend moving toward hyperlinks. That used to be Mentor, now it's Siemens. You have to keep track of all the the acquisitions. Siemens bought Mentor, and so it's Siemens hyperlinks, and it is, I think, one of the easiest to use system level simulators, and you can do a bunch of these transmission line driver receiver routing simulations with hyperlinks really well, and it provides really good graphical output, and it uses IBIS models for the drivers and the receivers. But to get started, to play around, to get a feel for things, the Symmetrics Elements, great tool to start with.
Okay, so I would like to I would like to use little bit numbers, because you always say like put there some numbers. So for everyone who is thinking like, okay, so should I simulate or not? I think what we could mention is like today's logic. Very often the rising and falling edge is, let's say, 5 nanoseconds or 3 nanoseconds, 8 nanoseconds. So it means you mentioned 1 nanosecond per inch. So inch is maybe like this. So maybe if it's like this, then maybe that's something what they should consider. Okay, maybe I could get this kind of signal, this kind of reflections.
Longer than that,
Yeah. So maybe I would like to simulate it. And problem with these reflections is because they may be quite high, it means they can actually influence what the input is reading, or what kind of value.
So there are two problems with ringing. One is the overshoot, and the overshoot means that the receiver is going to see a higher voltage than is being transmitted, and for a lot of the low voltage logic, the CMOS technology, there's a input gate at the receiver and really thin dielectric, and if you have too large a voltage, you could get a catastrophic failure, like an ESD damage almost, or it definitely hit the reliability. And so overshoot is a problem more for kind of the health of the devices. The undershoot is what can give you false triggering. And so you want to worry about the undershoot. Because that's going to pull what could be a logic 1 to a logic 0, or what was a logic 0 to a logic 1.
Exactly.
And the other problem is if the ringing lasts for a long time means a fraction of the unit interval, then some of the ringing noise from one bit transition leaks into another bit transition or another bit, and we call that intersymbol interference. And so there are multiple problems with ringing noise. And if you want a robust design, and it's not hard to fix the ringing problem, but if you want a robust design, you want to do what you can to reduce that ringing.
And also I would like to point out, even this ringing can be very visible if there is some kind of crosstalk. If there are some tracks routed very close to each other, then this ringing can easily spread also to the other tracks.
Yep. Usually if you have enough impact from crosstalk from ringing, the ringing itself is a problem on the aggressor line, and you got to fix that. And the fix is not very difficult. But your first point of when do you have to worry about it? So for example, in the PCB class that I've taught, we build boards that are about 4 inches on a side, and so the longest trace you're going to have is maybe 4 inches, and the signals that we use a lot of at the microchip 328 microcontrollers, the AVR microcontrollers, and their rise times are typically 3 or 4 nanoseconds. And with that technology, the interconnects are never really long enough to see ringing or from reflections. You see ringing because of ground balance.
Mm-hmm.
It's another issue, another problem, another root cause, another uh, uh, set of solutions, design solutions to fix that problem. But you don't see the reflection noise ringing. Um, the other thing that influences how much ringing, of course, is it's about impedance discontinuity. And the receiver, 99.9% of the time, is high impedance.
Mm-hmm.
And so you get a reflection from the receiver. When that signal goes back, reflecting from the receiver, and hits the transmitter, it's the output impedance of the transmitter that influences how much ringing you have.
Mm-hmm.
And for a 328 microcontroller, some of the other high current driver microcontrollers, the output impedance is like on the order of 20, 25 ohms. And so it's low enough compared to a typical impedance of a trace. Yep, you're going to have ringing noise. But if you have a low drive strength driver, like in a SAMD21 or something that can only deliver, like 3 or 4 milliamps of output current, typically those output drive impedances of the transmitters are like around 50 ohms.
Mm-hmm.
And so it's almost like being source terminated. And so even though you could have an interconnect that is long, you got to worry about reflection noise, it could happen, you got to worry about termination, knowing what your transmitter properties are is also really important. And so that's where, kind of looking in the specs, and unfortunately, a lot of the data sheets don't tell you, oh, the output transmitter impedance is, 64 ohms or 28 ohms. It'll tell you the drive strength. And it's sometimes difficult to translate that into, oh, what's that output impedance?
We can
So
make video about this, how to measure it.
yeah, yeah. And in
Yeah.
fact, one of the labs that we do in our class, in both the circuit board and our high-speed measurements class, is we reverse engineer what the output impedance of the driver is. And that's one of the ways of evaluating, okay, what is that impedance? When that signal, the reflected signal, comes back and hits the transmitter, what is that impedance that it sees,
Mm-hmm.
either in the high state or the low state?
Mm-hmm.
And we could talk about that sometime.
So basically,
But
I just would like
yeah.
to translate this. If someone is not like very into these impedances, what we are talking about is the transmitter will have some kind of impedance. Then there is PCB track, which is usually 50 ohms, and then there is input, which usually have very high impedance. And even if we have this reflection on the input and the signal is traveling back, the thing is, if our transceiver will have 50 ohms, same impedance what is on the track, then these reflections will kind of disappear. So that's basically what you mentioned. And I would like to say, I remember the times when people try to solve this with some kind of additional capacitors because they think like I'm going to filter
Slowing the
it or
edge down.
something. Yeah.
Yeah.
So what do you think
Yeah.
about this kind of solution?
Yeah. There are far more effective ways of doing it. It's in the old day, it goes back to that first rule of thumb about the rise time. If you don't need a short rise time, then yeah, you can slow down that edge so it's longer than in nanoseconds than the interconnect length in inches, and the reflections always happen. It's just they'll happen during that rising edge. They'll be smeared out. You won't see them. But I don't think any design these days has that timing margin available to use a longer rise time. We're typically, kind of push if you have such a long unit interval, you'll probably just use a higher clock frequency if the rise time is short enough. So yeah, I don't think that's a viable solution
So
anymore.
better solution is, for example, place series termination resistor close
It's
to
about
the
terminating, right?
output. And if the output is, let's say, 20 ohms, and then if we put there 30 ohm resistor, we will get 50 ohm uh,
Right.
transmitter impedance, and then that's what we would like to have.
Right. And we call that source series termination. So if rigging is a problem, then it's all about a termination strategy. And there are, I think, 5 or 6 different termination strategies to take advantage of. But you got to first recognize ringing is a problem, identify the root cause, and then decide which strategy you want to use
Mm-hmm.
based on cost, power consumption, and kind of signal to noise or margin in the result.
And this is the reason actually why many times people may see 30 ohm resistor on some of the lines, clock
Yeah,
lines, for
right,
example.
right. Yeah, and a lot of the higher end DDR4 and above, and a lot of FPGA and a lot of ASICs will use on-die termination. And that is always going to give the best result, because the parasitics, the inductive kind of the property of that terminating resistor, it's a resistive element, but when you physically build it, it's got some inductance and capacitance in it, and it doesn't look like a resistor above, gigahertz or so. And if you do it on die, that'll give you the highest bandwidth terminating resistor. Uh,
Okay, so let's talk about this.
yeah,
So we would like to confirm there will be no this kind of problem on our board. What is the next step?
right.
Simulate it.
So simulation is always a really straightforward thing to do. And, we mentioned some, symmetric elements as a free tool. And it's not a very large learning curve. Maybe another time I can do a video with you, or put one on your site, about how to get started with symmetric, because it's really easy, and we can set up some of these kinds of circuits and simulate ringing. And you can, I love working with simulation tools. If you understand what you're doing, simulation tools are, I call them virtual prototypes, playing a sandbox. You can do all sorts of different varieties. You can explore design space, and it's as though you were building, if you have confidence in the tool, and that's what we're going to talk about here. If you have confidence in the simulation tool, then you can use a simulation tool as a virtual prototype to try things out and see what happens. Kind of exercise your understanding and your intuition. I always tell my students, and every professional engineer, that you never that you can screw up a simulation just as easily. Well, I can screw up a simulation just as easily as I screw up a measurement. Lots of ways of going wrong. And so you want to use your engineering judgment when you do a simulation to first have confidence in the result, think about the result, apply rule number 9. I think, am I wearing my rule number 9 hat?
Yeah, yeah.
Yeah. And think about and apply rule number 9, so that you have confidence. I can trust the result from this simulation. And if you can learn a lot before you build something of how it might behave. And part of that question is, how do you have confidence in the simulation tool?
Yeah, this is good question, because I remember everyone is saying simulate it, simulate it, simulate it.
Right,
But how do you know you set up everything correctly and you
right,
interpreted the results correctly? So what do we need
right.
to set up in this kind of, this is one of the simplest simulations. So what kind
Yep.
of things we need to set up?
Right. And so I apologize, I don't think I have the actual circuit, but it's a really simple circuit. So the question of how do you gain confidence in simulation tool, there are really kind of 2 steps. The first is, you want to simulate something for which you know the answer. So that you can verify, yeah, it's giving me what I expect to see, and I have really good confidence of what I expect to see. So you pick a circuit where you can do the calculation of what you expect to see by hand. So you build a simple source, ideal source, we use a Thevenin model for a source, which is simply an ideal voltage source step edge with a series resistor. That turns out to be an incredibly good model. It's really simple, and it's a really good model for almost all transmitters. And so it's a ideal voltage source with a series resistor as the source. You build a simple transmission line, ideal lossless transmission line, and then your receiver, which typically a high impedance. And so that's where you put the scope probe. And that is as simple as it gets. And that's basically a really good way of modeling a real transmitter, trace on a board, and the receiver. And that's kind of what we've done in this example, almost that exact model. Um,
Very often you can also download some models, no? Or
so IBIS models. The challenge, of course, there is, how do you know what the quality of the IBIS model is? And if you're dealing with something like a uh, a microcontroller, or if you've got a specialized, even a 555 timer, or you've got a hex inverter, or you've got some oscillator, you can download a model for that component, run it in the SPICE, but it always kind of begs the question, well, your simulator may be a great numerical simulator, but the quality of the result is only as good as the quality of the models that you use. And so again, it's part of that. How do you gain confidence in the quality of the model? So I said, two things. First is simulate something for which you know the answer so that you can verify, yep, it's exactly what I expect to see. And the second is, if you really want to get good confidence, you want to build a system that is well characterized so you know what its features are, and then measure it and compare the measurement to the simulation.
Mm-hmm.
And that's what we're doing in this case. And
Mm-hmm.
if you download an IBIS model or another transistor-based model for a functional device, then you want to, they're often built based on nominal properties. And so there's sometimes a wide range of processing conditions when that chip is fabricated, so that the behavior of your actual device, it's not exactly the same as the behavior of your real device. The DC levels might be the same, but the transitions, rise times, the ringing noise may not be the same. And so if you are really committed to, I want to have a really good, I want to have confidence in my model, you'll purchase or build a little eval board of that component, and you'll measure it, and you'll compare the measured result, the waveforms, the rise times, the timing of that real device compared to what the SPICE model or the IBIS model gives you.
This is very interesting because I was always like, these IBIS models, they have to be good. It's
Well,
like,
yeah, you would expect that, but unfortunately, um, it rarely will. I think my professional opinion is, and I tell this to all the vendors, I work with a lot of the tool vendors out there. I tell them it's their responsibility to not only produce a quality model, but equally importantly, provide the verification of the accuracy of their model. That when a semiconductor company sells you a part and they give you the IBIS model or a SPICE model for it, they should provide a data sheet that shows, here is one of our parts, here's the part number, here's the lot number it came from, here's a measurement of its output waveform, here's the simulated waveform, and superimpose them on the same plot. They should provide that, but they don't.
mm-hmm.
And but it's a really good exercise. I have my students do that all the time. That's one of the examples we're going to show here. And it's possible to reverse engineer that model to convert it into a really simple Thevenin model as well, and use that in your simulation if you have confidence in it. So confidence in the model, the device models, really important to get. If it's rare that an engineer that has a deadline for product development, it's rare that you have the time to, "Oh, I'm going to buy an eval board and I'm going to set it up at my lab and I'm going to go do a measurement and get the model and I'm going to simulate in SPICE and I'm going to compare it." It takes, a week to get the device, a day to set it up, do the measurement and the analysis. And that's, a day that you're not going to be optimizing the product and shipping it out the door. And that's where third parties come in. That's where that's what we try to do in our lab at University of Colorado in Boulder. Is we try to teach our students how to do that so that they have confidence in some of the models that they use.
Mm-hmm.
But I think that's where customers that are buying parts should be insisting from their vendors, "Hey, show me why should I believe your model?"
Okay, so let's talk about these slides what you have here. So the
Okay,
first one is the
yeah.
simulation, correct?
Yeah, so let me show you the setup.
Okay.
So we're doing a measurement of a system. And in this system, can you see my mouse
Yes, I can
moving?
see your mouse.
Okay, so this is a simple board that we use in one of my classes. This is our high-speed measurements class because it involves transmission. So we distinguish circuit board design and high speed is when you have to worry about transmission lines and reflections, that's high speed. Otherwise, you got to worry about ground bounce, you got to worry about rail collapse. Those are the two important design considerations in any board design. And then as that rise time gets shorter, interconnects get longer, you reach that transition where reflections play a role. And so this is looking at the reflection problem. And so to enhance the problem, so we call those pathological. So we wanted to create a pathological condition so it was really easy to see the problem and understand it. And so we took a hex inverter, and its hex inverter is 6 inverters. And so we gang them up so that to make pathological, we wanted the absolute worst case. We wanted a really low output impedance transmitter, and we wanted a really off impedance transmission line going into the open of the scope, high impedance of the scope. And so we have a hex inverter. We've taken all 6 of them and paralleled their outputs, and their inputs are all in parallel too. And so we use a little clock chip over here. We generate I don't know, I think it's like a 10 kilohertz clock frequency, and the edge of this triggers the input to the hex inverter, and so it just inverts it. And so we're going to see a square wave coming out with a really low output impedance, like 3-4 ohms.
Because
really
they
low
are
output
all in
impedance.
parallel, so
All in parallel. And so they're typically about, I think it's about 15, 18 ohm output impedance for each one. And when they're all 6 of them in parallel, it's 1/6 of that. So it's like 3 or 4 ohms as the output impedance. And then we have this, I don't know if you can see this really long meandering transmission line here. So it's really long. So again, we have the rise time of the signal, I think it's like 2 or 3 nanoseconds. And that says anything more than like 3 or 4 inches is you're going to see ring. And so we wanted to, again, pathological, really make it extreme. And so it's like 20 inches long if you unwind it.
And it's 50 ohms or?
Well, actually on this particular one, really high impedance. So this is I'm trying to remember, I think this is a 2-layer board, and we're using like a 6 mil wide line. And if you put in the numbers for 6 mil wide line, 59 mil thick dielectric, it's like 130 ohms, really high impedance, right? Again, pathological. We wanted to make the big impedance mismatch between the driver, the transmitter, the transmission line, and then it open at the end. And so here's that meandering path over here, and then we go over here, and here's our test point, and this is for a 10x probe test point, and the 10x probe is to first order really high impedance. It's at DC it's about 10 mega ohms, but as you go up in frequency above about 10 kilohertz, it's not really looking like 10 mega ohms. It actually looks like a capacitor. And so to second order, we want to include that capacitance of the 10x probe. But first order, just high impedance. And so this is the circuit. So we got the clock chip driving the hex inverter, all of them in parallel, going through this long transmission line, and we're going to measure the 10x probe. And so we're going to see, rule number 9, we're going to see ringing. As the signal comes out of this, it sees this really low impedance. It sees the 130 ohms of the transmission line. We get most of that it's a voltage divider, 3 ohms to 130 ohms. Most of that voltage gets launched into the transmission line, travels down, and then hits over here. And when the scope probe is plugged in, it sees effectively an open. And so it's going to reflect, and it sees, okay, now I get that, roughly, I can't remember, is this 5 volt, 3 volt? No, this is 3.3 volt. So 3.3 volt goes down the line, hits the open, and what happens at the open? Well, 3.3 goes in. How much is going to reflect, do you think?
3.3.
3.3 is going to reflect. And so what does the receiver see? What's the voltage of the receiver sees at that instant?
6.6.
Yeah, it sees 3.3 go in, 3.3 go out. It sees both of those, and it's going to see 3.3 or 6 volts. And then that 3.3 volt signal reflects back, and it goes back through here, 3.3, 3.3, 3.3, and now it hits the transmitter, and the transmitter is like 3 ohm. And I go from 130 to 3 ohms, it's almost like a dead short. And so it's going to reflect. But the reflection coefficient when you go from a high to a low impedance is negative. And so that 3.3 hitting there reflects with like minus 3 volts. And so minus 3 volts reflects, minus 3, minus 3, minus 3, and hits over here. And what happens when minus 3 hits there? It's going to reflect. I had 6 volts, 6.6. Now I have minus 3.3, and it's going to reflect as minus 3. So I have minus 6 volts. And so let's see, 6.6 minus, it's like a half a volt. And so I'm going to go drop down to like half a volt. And then
That's
I
what we
get
see.
minus, huh?
That's
Yeah.
what we
And so
see there
minus
on the red graph.
minus 3, yeah, exactly. So here's the actual measured voltage. And so here's the initial voltage I see. It's at 6.6. That positive 3 volts reflects back, hits here, reflects as minus 3, heads back this way, and it pulls down like minus 6. And here it is, minus like 0.7 volts, something like that. And that minus 3 reflects, hits here, changes sign, reflects as like 2.5 volts, comes back here. Now I'm going to see another 2.5, 2.5, that's 5 volts. So it was like a little like 1 volt added to 5 volts. There's 5.5 volts, reflects, changes sign, and so we see the ringing, right? So it's all the reflections back and forth. And even the absolute, this is literally the simplest circuit you can have that shows ringing. Low impedance driver, transmission line, high impedance receiver. And even that is really complicated, keeping track of all those reflections. That's where simulation is really important. And any SPICE simulator will simulate this. And so this is the measured voltage. So we literally measure it on a scope. We take the scope measurements, save it as CSV file, bring it into our simulation environment, and replot it in the simulation environment. And that's what we're doing here, replotting the simulation environment. And we see the ringing. And look, oh my gosh, it lasts for a long time. And why do you think it's stamping? Why do you think it's dropping off like that?
Because
What's making it drop off?
Because the reflections are not like 100%.
Yes, exactly. Because every time it reflects from here, we get most of it reflecting. Every time it reflects from here, well, it's not a reflection coefficient of -1. It's like minus 0.93 because it's 130 to 3 ohms. It's not to 0 ohms. And so every time it reflects, we lose a little bit more. Exactly right. What's another explanation for why it damps off? Why does it drop off?
Do you know?
So, I ask my students this question all the time, right? And 90% of them say, oh, it's the losses in the transmission line. That this is a result of the attenuation in the transmission line. So that's another one on the list. And there's a third explanation as well of why it keeps dropping off, why it drops off like this. Can you think of a third explanation?
I couldn't think the second one, so
So, well, most of my students have taken high-speed digital engineering or design, so they're familiar with lossy transmission lines, and that's the first thing they think of. Oh, it's losses in the transmission line. There's another factor, and that is, I said at the receiver here, I'm sticking the 10x probe, and to first order, it's just a high impedance resistor, but to second order, it's a capacitor, and the capacitor is going to, like you mentioned before, it's going to increase the rise time of the signal. It's going to slow the edge down a little bit. It's going to make it more slopey. And more slopey means it's going to not reflect as much. It's going to smear out the edges a little bit. And so that's a third factor. And the question is, which one is it? Is it the difference in the rise time of or the difference in reflection coefficient because it's a 3 ohm output impedance? Is it the losses in the transmission line? Is it the input capacitance of the 10x probe? Which is causing that drop off? And this is where simulation can give us insight. Because in the simulation tool, if we have confidence in it, we can play the what if games. We can tweak the knob of, well, how big an impact is the losses? Turn the losses off and see what the impact is. Or turn the losses in the board on, make it extreme. What's the impact? Or change that output impedance and what's going to be the impact? Or change the capacitance. And so this is where measurement simulation correlation is so valuable because it lets us play those what if games to understand the real root cause. So that's the setup. We do the measurement and now we build a model. And the model that we use is really simple. So instead of, if you use an IBIS model or a SPICE model for a component, Both of those are, you get them from the vendor, and you put them in the simulation tool and you push the button and you get an answer. But there's no knob to tweak. You can't, we call them point solutions. They are for that specific case, and I don't know how well they apply to my device here that I have on my board. And so while it's always a great starting place, they use kind of effectively nominal values for the component. I can't explore design space much with them. And so I always like to recommend starting with a model that is parameterized so you can make some changes. And that's where the Thevenin model for a transmitter is so valuable, that it's a really good first order model of almost every transmitter.
Do you
And
have
you can
this
always,
model in detail somewhere on these slides, or?
you know what? And I apologize, I don't. I didn't write it in here because this is a presentation more about measurement, simulation, correlation, and I'm just showing this as an example. But I am sure we've talked about the model before, but it's really simple. Let me see, can I draw on this? I don't have my touch screen interface here. Let me, okay,
Maybe we can Google it or something.
Well, yeah, actually, I was gonna try to draw it here. Let me do this. I'm gonna do this. I'm gonna clear this screen here. And now I think I have some drawing tools. And so here, let me draw it. So here's the voltage source, ideal voltage source. And here is a single ideal resistor. So, you know, whenever you do a simulation, whenever you build a model, it's always ideal elements, right? And this model, so here's the voltage source. And we're going to use a voltage source that has some rise time to it. So it's got a starting voltage here. It's got a final voltage here. In this case, it's like 3.3 volts, something like that, 3.3 volts. And it's got a rise time associated with it. And those are parameters that you can set in the voltage source. And then the output resistance has another parameter, the resistance. So it's parameters. I can explore design space with that. I can make some changes and see what the result is. And this is what the transmitter looks like. And then the rest of the circuit for the transmission line, it's literally an ideal transmission line. And now, if we want to explore the losses in the transmission line, then we need to include a model of a lossy transmission line. And this is where different simulation tools vary, because not every tool has a good lossy transmission line model. LT-Spice doesn't. Symmetric, as much as I love it, its lossy transmission line model just has is not a very good lossy transmission line model. Quix, one of my other favorite free simulation tools, has a very good lossy transmission line model, has dielectric loss in it and conductor loss. And then Hyperlinks, of course, does. And my other favorite tool, ADS, Keysight's ADS, has a really great lossy transmission line model in it. So if you want to include an effect, you got to make sure that the simulation tool supports ideal elements that have that effect in it. And so, but you can start out with just a simple uniform lossless transmission line.
So that's like, there's only connection basically in your simulation.
Well, so there are two parameters that define a uniform transmission line model, a lossless
Delay.
transmission line. The delay, the time delay is one, yep. And that effectively is like the length, the electrical length. And what's the other term that defines it?
Losses, I don't know.
The characteristic impedance.
Impedance, okay.
And you need that because that's why you have reflections. If you use just a wire connection, so here's my receiver, and my receiver, I'm going to model as just a really high input resistance, 10 megohms. And then here's the ground connection, and then here's the ground connection over here. And so I'm going to use a really high impedance. And if I made this connection here, then if I use just a wire and didn't use a transmission line, I wouldn't see any reflections. It would just be whatever the output is, that's what I'm going to see. It's the transmission line and the impedance difference at the two ends. So I'm going to put an RX over here just to remind us, okay, that's at the receiver, and this is at the transmitter here. This is, this circuit model that gives rise to those reflections, what we were talking about.
So this is the simplest simulation.
Simplest one you could do. perfect in symmetrics. LT Spice even will let you do this.
And basically
And
I'm sorry for interrupting.
yeah,
Basically
go for it.
the trace element, it's one of the elements which you can pick and place into your simulation. Yeah? Like the
Yep.
voltage power supply, resistor, then one
Yep.
of the elements
It's
will be
called a
this.
T line.
Mhm.
A T element
Okay.
is what it is, that universal in all Spice tools.
Okay.
And this will predict that ringing for you. And with this, you can explore, how does the length of the transmission line and the rise time of the signal, how does that play a role in the reflection? So you can probe the point over here at the receiver. There's a probe point. You measure that with the, or you display that voltage there. You can see the ringing noise. You can change the rise time. You can change the length. You can change the impedance mismatch between the source and the impedance of the line. All those things you can play with this virtual prototype, right? And that's the starting place that we used for this model. And this is what you get. And so
That's the blue
using that,
line, yeah?
that's the blue line,
Hmm.
right? And so the red is the simulated result. And I try to, so I use individual points here, you can see in the measurement or in the display, to designate, oh, that's measured results. Each one is a voltage point the scope measures. And then the blue is what the simulator tool predicts.
Hmm.
And this was based on, so in order to do the simulation, you have to know, okay, the level value, okay, we guessed that.
Hmm.
You have to know what the rise time is. We guessed that
Hmm.
based on our estimate nominal value. We have to know what the source impedance is.
Hmm.
We guessed that nominal values based on what we thought the output impedance was. The characteristic impedance, the time delay, we guessed that, and we used 10 megohms over
Hmm.
here for the input. So we started out with values based on our best guess. That would be dead reckoning. If we didn't know anything else, here are the nominal values that we're going to put in. And, here's what we got. Not bad. You know what? For most applications, this would probably be good enough. And so dead reckoning is pretty good if you have, some idea of what to expect in your design. Well, but you can see, well, we don't get all of the overshoot, we don't get all the undershoot. And, if we had guessed a little wrong and, the impedance was actually lower, probably could have gotten higher values. But look, we got the 3.3 volts really well eventually. And the damping, we kind of got that sort of. So it's not that bad a guess, but that's when we guess. And now we did two other things. The first thing is we looked at that rise time of the signal with the scope, and we zoomed in on this edge so we could measure what was the rise time.
Hmm.
And we had a good measure of that. Then we measured the output impedance of the voltage source. And here's how you do that. It's really, really simple. This guy is on. I mean, we're in the measurement. We're zooming in. This is in half a nano. This is basically a half a microsecond. We're zooming in. But the period was like 100 microseconds, 10 kilohertz or so. So we had 100 microseconds, how long it lasted. And so in this case, we looked at this region here where we got the DC value, and then we looked at it open, which is what this is. That's 3.3 volts. That tells us what, if you have a Thevenin circuit, there are two terms that characterize it: the Thevenin voltage, Thevenin resistance. We get the Thevenin voltage by looking at the open circuit voltage. And then we literally took a resistor, and I think we used 50 ohms. We connected a 50 ohm resistor across the output, and we measured the voltage with 50 ohms. And so now we have 50 ohms over here. We measure the loaded voltage coming out at steady state. And we know what this voltage here is. We know what this resistance is. We know what this voltage is. Hey, it's a voltage divider. We can back out what this has to be. And so we were able to directly measure the output resistance of the driver, both in the high state and the low state. In the low state, you have to add a bias voltage to it, but very straightforward to do that. So we directly measure that output Thevenin resistance. So now that's not an unknown. We have confidence in it. So we put that value in. And now at the receiver, so we know enough, and one of the exercises I have my students do is we actually literally measure the output impedance of a 10x probe with the network analyzer. So we measure its impedance profile with frequency, and if you know that, you can fit a model to it, so it looks like a a 9 meg resistor below a kilohertz, and it looks like a 10 picofarad capacitor, up to a couple hundred megahertz. So we know the model for our 10x probe. And so we put that in. So we took this and we said, okay, I know what this is, but you know what? There's also a 10 puff capacitor over here. And so we put that in. And so we know what this is. It's not a variable anymore. We know what the rise time is. It's not a variable anymore. We know the voltage is not a variable anymore. We know what the probe is over here. And then we said, okay, you know what? I'm going to look at what the impedance of this line is. So in order to calculate, if I know the geometry, in order to calculate the characteristic impedance, I need to know also the line width and the dielectric thickness, but I have to know the dielectric constant of the material. And so, part of what we do in our class is we build test boards that we send to our vendor. We use JLC PCB, we use PCB way, and we send them test boards. We get them back, test boards that are designed to measure the dielectric constant. And we could do that on another presentation because there's really simple technique and it gives you a very good, very quick, easy measurement that can be done with very simple equipment. And so we measure the dielectric, and we know it's 4.9. For the 2-layer board, when you have a core, it's 4.9. And so now, now we don't have to guess the dielectric. We know what it is. We know what the line width is. We know what the thickness is now, and we know the length because we just, count the length in Altium in the design tool. And so we know what the line width, we know what the length is, we know the stack up, we know the material properties. No guessing anymore. We just put those numbers in here. And we used a lossy transmission line model so we could vary the most important term that influences loss in a transmission line is the dissipation factor of the material. And so we could make that, I didn't know what it was. I know what it is, but in this example here, we were going to make that a variable to see what its impact was. And so we added a lossy transmission line model that had the DF as a term in there. And we started out, we said, okay, let's turn off the DF and just see, does it matter? Does it play a role in this simulation? So again, one of the principles in any measurement simulation correlation is always start with the simplest model possible that has the features you want. And then if you can't get a good match, then build complexity in there. That's why we started out with no capacitor over here and no loss over here. Simple. And so we turned it on. And oops, wrong one.
So basically, DF is the only one which only unknown variable in all
right.
these.
And there's also the resistance loss in the line, and we could turn that off as well. But I have enough experience that the dissipate at these frequencies, the dissipation factor is an important term. Oops, wrong one. Going the wrong way. Here we go. And so this was dead reckoning, just best guess what we thought. And then we made those changes. And all we did, we used the output impedance that we measured directly. We used the input capacitance of the scope probe we measured independently. That was our model. We used the dielectric constant that we measured on test boards. And here's in blue. And we used dissipation factor 0. And you can see that, oh my gosh, we were able to account for, I mean, that is pretty darn good match between measurement and simulation correlation. And so it says, you know what? We understand the system really well. Now we can play the what if games with it. And so we turned on the dissipation factor. We made it, for FR4, a good starting nominal value is 0.02 dissipation factor, 0.02. We turned it on. We saw virtually no impact at all. And so that's how you use this kind of a simulation. It helps you answer some of those questions of how important each effect is. How important is the dissipation? Well, in this case, all of that damping is from the impedance mismatch at the transmitter. And it turns out a little bit of it is from the capacitance of the probe. That when you turn off the probe capacitance, it's not quite as good a fit. And so the probe capacitance is important. And partly because we have such a high impedance of the transmission line, it's more sensitive to the input capacitance of the probe. But it says, oh my gosh, really, all those complicated second order factors, the package model, the bends that, even we use rounded bends because it was easy to do to an Altium, there's a tool that does, give me a meander and it just comes out that way. But if we'd use square corners, you say, got to include the bends and the square corners. What about the parasitics of the scope probe here? Or what about the distortion of the rising edge of the 10x of the hex inverter? You can make a list of all those second order things that you worry about. Well, doesn't that affect it? Doesn't that affect? Doesn't that? We didn't include any of those in this simulation, and it's pretty good. Now, it's for 3 nanosecond rise time. So if you're dealing with 224, I kid my students about it. These are really important principles. But if your system is a 224 gigabit high-speed serial link with a unit interval of 18 picoseconds, and your rise time is 2 picoseconds, yeah, you got to include all those effects. But that's where engineering judgment comes in to decide how important are the second or third or fourth order effects in simulating your system. So it's where experience comes in to decide. But that's why I say always start with the simplest model possible, build complexity from there. And so it allows you, once you have that confidence, it allows you to see what is the impact of, if you turn off the input probe capacitance, do you see any impact? And the answer is yes, you do. So it turns out that's important as well. The time delay, of course, influences, which is related to the length and the dielectric constant, influences the ringing frequency. And when you nail the dielectric constant, wow, really good match of that ringing frequency. The impedance of the transmission line and the mismatch with the output impedance, really important. That influences the peak head here. And you can tweak each knob in the model and you can see its impact in the simulation. So that is just an example. And it's a really simple it's kind of like training wheels in order to do measurement simulation correlation. And you can't, if you had an IBIS model for the transmitter, for example, then you wouldn't have this opportunity to tweak the output impedance. You'd use what's there. And you would never really know, is this because of the impedance of the transmission line, or is that because of the impedance of the receiver, for example? And that's why I like being able to use a parameterized model to explore design space. So really simple example. And then here's one other example of using measurement simulation correlation and using it to help answer some of these what if questions. So here was another board example. This is one of my students, group of my students did. Because I've often said, and I think we've talked about it, I've done it in a bunch of other presentations, this idea of copper pour. I see it on all the designs. Everybody adds copper pour to their boards in blank areas. And when my students do that, I ask them, why do you have copper pour in your signal layer, your copper fill? Why do you have there? Well, that's what this other design did. Or I'll ask an engineer that, well, that's what our other engineer recommended we do. Nobody has given me a really good explanation for it. And when I do find someone that has an explanation, they say, oh, copper it's a really good conductor. It'll shield all the stray electric fields, so I'm going to get lower noise with it. So we did this project a number of years ago to demonstrate, is there an advantage in copper pour or a disadvantage? And again, we went into it with an idea, because I know if I have isolated piece of copper and I have trace going nearby, and isolated copper, another trace, I know I get resonant coupling into that floating piece of copper. It is a resonant source, floating transmission line, basically, and open at the ends, and so I get reflections back and forth, and it's just floating. And so I know that if I have isolated copper, number one, I don't think it's going to do any shielding. Number two, if you pull the traces far enough apart in order to put the floating copper, you've automatically reduced the crosstalk by doing that. And so I think that adding floating copper to a board adds more problems than any that it fixed.
Floating, it means it's not connected to any net.
Right. It's
Okay.
not connected. Even if you add ground vias and you think, oh, I'm just going to stitch it to ground, it turns out that unless you do it really, really well, meaning, a lot of return vias, all the different places, it adds more noise.
That's what I see on your board, no? I think the board, what is there? There are only 2 vias, then 4 vias, and then
So here's
8.
the board. This is just the top view. There, you flip. It's a 4-layer board. You flip it over, and then here's the bottom side.
Yeah.
So on the top side,
Oh, okay. I see. There are 5
here's what I've got.
examples.
Yeah, 5 examples. And so this is 2 transmission. So this is using, I think it's like 6 mil line in space or something. It's 4-layer board. In order to get 50 ohms, it was like, maybe it's 8 mil line in space. And so to fit another trace in between, we have to pull the traces 3 line widths apart, right? And so that's what this is. This is the 2 traces 3 line widths apart. And this allows us to measure the crosstalk between them. And then this is adding the isolated copper fill between them, right? And so this is just isolated copper, that's all. On the bottom side of the board, we have the same structure as this, but here we've added 2 stitching vias to the ground plane. Here are like 4 or 5, and here's like 11 stitching vias to the ground plane, okay? So those are 5 different examples. And so we did the measurement, and we did it with the network analyst. We measured S parameters. That's a really convenient way because you can look at the bandwidth of the model. But I'll just explain what we're looking at. So this is just an example. So we're going to look at let's see. So here's the case of this is case 2. This is copper poor. So this is the worst case, and we're looking at the reflected signal. So we have 4-port measurement. We're going to send a signal in one of these lines. It's going to travel down, it's going to hit the end, it's going to see 50 ohms of the other port, no reflection, right? So nothing should come back in principle. But okay, the transmission line isn't exactly 50 ohms. I got my crappy, these are 20 cent SMA launches on the ends, and so there's reflections from the end. It's not exactly 50 ohms, so you get a little bit of reflection back and forth on that line. In addition, I've got this floating metal nearby. And when the signal travels down that transmission line, there's crosstalk into that floating piece of metal. And when the energy gets into this line, what's it going to do? Well, it's a signal on that line. It's going to propagate, hits the open ends, it's going to bounce around, and I'm going to hit resonances in there. And when I have resonances, some of the energy that is bouncing back and forth is going to recouple back. It's going to pollute the signal line over here. And so at the resonances, energy gets coupled in here, and some of that comes back. And I see that as when I send the signal in, here in red is what's measured. And, there's low frequency. Here's a gigahertz. So relatively low frequency, minus 30 dB. That's very low return loss. Not much is coming back, right? But when I hit, here's 1 gigahertz, here's 2 gigahertz, here's 3 gigahertz. Oh my gosh, when I hit this is a 3-inch long line. And so the resonant frequency for 3 inches is 1 gigahertz. When I hit its resonances, I get enhanced noise coupling back, and that looks like more signal reflected. Looks like it's not a discontinuity, but it looks like more signal reflected. So we see that as number 1 problem. Now we look at crosstalk. So I send a signal in this line here. I look at the noise that's coupled over to this guy over here. And I don't, this is from a different talk, so I don't have the example of, I do later. I'll show you with no, I'll show you this case here with no other trace between. The crosstalk is very small. With that trace in there, look, I have enhanced crosstalk. So here at 1 gigahertz, 20 dB, minus 20 dB is the crosstalk. Do you know how much voltage minus 20 dB is?
No.
So it's 10%. So if I were to send a 3.3 volt signal in here, and I had a 3-inch long floating piece of metal here, in this other line that's 3 line widths away, I would get 300 millivolts of crosstalk at 1 gigahertz. I see ringing noise at 1 gigahertz.
And it's because basically the resonance is there because the length of the line is exactly the right one. Basically, when we are putting there another wave, it's building on the top of the wave which just arrived.
Yep.
Okay.
It gives me a half a wave. The length of this line corresponds to a half a wavelength at at 1 gigahertz, and I build up that wave in there, and it pollutes back into the both ends. It goes back to the source, and it comes back to this poor victim line sitting here. And so look at the, so here is dead reckoning. Here is, we literally took this geometry and we brought it into our simulation tool. Because again, we knew what we measured the dielectric constant elsewhere. I know the geometry, and that's it. If you know the geometry and you know the material properties with an electromagnetic field solver, you can predict, it's a virtual prototype, this structure. And the blue is what we measured. And you can see, oh my gosh.
Blue is simulated, no?
I'm sorry. Yeah, thank you. Blue is the simulated. Red is what's measured. Look at that match. It's incredible. Up to 10 gigahertz here. Again, if you know the material properties and geometry and a good field solver, this gives you confidence. Wow, I've included everything that's important. And then here is the far end crosstalk. And again, there's no fitting. I'm not adjusting anything. I'm literally just taking the geometry that I know as designed and the material properties as measured on test coupons. And really good match. Gives you confidence in the result. And now that we have confidence in the tool because of the measurement, simulation, correlation, now we can play the what if games. And so now we do that example. We build that same structure, the aggressor and the victim, we add the copper pore, and now we can change the geometry, anything we want. And so we said, okay, let's pull the two lines really far apart. So it's a 10 mil wide trace. We pull it really far apart, and we put copper pore in there. And let's compare the crosstalk. If we didn't have the copper pore, we just had the traces far apart, right, sitting on the board. So here is the simulated far end crosstalk. So with no copper pore, we're already down at minus 40 dB. I mean, that's 1%. And that's into the, and it's below this minus 60 dB or minus 50 dB at 1 gigahertz. That's a 0.5%, 0.3% minus 50 dB. So it's already 0.3%. Who cares, except the extreme cases at a gigahertz there. So with no copper pore, this is what we got. With copper pore, we were up to minus 25. That's 5% crosstalk. That's 5% crosstalk. So adding the copper pore on your board, you have gone from something that is below 1% to something that's 5% crosstalk. Why add copper pore? So that's where, and then if you say, well, okay, I didn't do it right. Let me add shorting vias. Okay, so I add shorting vias here through the copper pore. That's in green. The difference between copper pore with shorting vias, it's pretty darn small. And at that level, especially since it's minus 50 dB, I'm not sure I believe it. They're basically the same. And look, as I go above a couple gigahertz, even with the shorting vias, it's still worse crosstalk than with no copper pore at all. And so what's the argument of using copper pore? I don't know.
Okay, I would like to explain this a little bit because I know some people maybe they don't fully understand what we see on this graph. So I would like to say like this means that for some frequencies it may be fine, but for other frequencies there may be problem. So fine, it is for the frequencies which are in the lower points, and it will be bad for the frequencies which have the very high peak.
And if you're using wideband signals, digital signals that have bandwidths in this regime, then you're going to see that the impact of this is ringing in the time domain. And we can do, I can show you the rest of the presentation of this where we talk about and we show the time domain signals, and you can see the ringing that's involved. But if you have Bluetooth, 2.5 gigabits per second, I mean, or if you have signals that have, a gigahertz bandwidth, they're using all of this frequency range here. And look, it's all a factor of 10 to 20 times more noise than if you didn't have the copper pore. And if you have Bluetooth signals at 2.5 gig, depending on the length of that copper pore, you could be 2.5 gigahertz at one of those resonances, and you could have 100 times more noise in your system because of adding copper pore than without copper pore.
Mm-hmm.
And so that's why I always say you better have, interconnect design is first about connectivity, making sure everybody's the terminals and you're getting the net list created correctly. And then it's about reducing noise. And so you have to ask the question, when you add a feature, what is the problem you're trying to solve? When you add copper pore, what is the problem you're trying to solve? And if you think that it is solving crosstalk, I think you're wrong. I don't think it's solving
There may
crosstalk.
be better solution like putting tracks away than
Yeah,
trying to
right.
put their
And so that's where
ground.
you have to do the analysis to see, is it do you have a crosstalk problem to solve? Blatantly just, or as a blanket solution of just adding copper poor everywhere on a board is a very dangerous path to take. And again, we analyze that using a simulation tool if we have confidence in the simulation tool. You know, I always say
Yeah, go ahead.
you push a button in a simulator, you're going to get a result. But it's that question of, do you have confidence in the accuracy of that result? Do you want to base your design decisions on it? And that's where doing the things we talked about are really important. Simulating something you know the answer to so you can check it, and then simulating something that you have that's well characterized to gain confidence in that tool, really important.
My last question, because we don't have much more time. So what is really bothering me, go back to previous slide, 18, slide 18. So basically what we did here is, this is the signal when we connect the scope, but that's not the signal which is really on our board when the scope is not connected.
Ah, very good, very good. You're absolutely right, because when we looked over here, we connected the scope probe, and the scope probe had basically a 10 picofarad input capacitance. The receivers, depending on the receiver, it'll vary, and depending on, if it has ESD protection diodes in it, it'll be something in the order of about 2 to 10 picofarads. And so it's not so far off, but because we have the model for it, now we can, if we know what the input gate capacitance of the receiver is, we can change this and see what the impact is. So you're exactly right. That's where the receiver model is really important. And the most important term in most receivers, if it doesn't have on die, most receivers are really a capacitor. And so if you know that one parameter for rise times in the nanosecond and longer time frame, if you know that one parameter, you have a pretty good idea of what that model is for the device. And you can get that if you open up an IBIS model and you look at the term in the IBIS model is called the C-comp. And if you can find the C-comp value, you'll see it typed in there. It'll generally be in the 1 to 5 picofarad kind of range. And then there's the pad capacitance of the board. And so one of the experiments I have my students do in their high-speed lab is we take a hex inverter and we take its input and we measure the input gate capacitance using TDR. And we can measure the pads on the board. We take the part off, we measure the pads on the board, we'll put the part back on, bias it, and then we measure the input gate capacitance. And it's about 5 puff. So knowing it is really important. And if we know it, we can literally take this off and put the value in, and now we can simulate what the receiver
you will
would
see what really is happening on your board.
Right. It's what we call virtual probing.
Okay, because I wanted to point out this, because many people, they think when they probe their boards, that's exactly, these are the signals what are really traveling to the board. But
right.
Sometimes when I see what kind of probes they use or what kind of scope they use, actually they may actually see something completely different.
Yeah, right. And that's where the probe that you use is important. Most of these 10x probes, the bandwidth we used here is about 500 megahertz. It was higher. The scope bandwidth is 200 megahertz. That's why rise times shorter than about 3 nanoseconds would be distorted a little bit. It would be slowed down a little bit with the scope, but the bandwidth of the probe was higher than the scope bandwidth, so it wasn't limiting the result here.
Mm-hmm. Okay, thank you so much, Eric, for explaining this. I would like to ask everyone if there are some topics what we maybe could make videos about. Leave them in comments, and then we will find time to talk about them.
Yep, great. Hey, always a pleasure chatting, and look forward to doing some more of these.
Okay, thank you, Eric.
Okay, bye-bye.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.